let's see, we've done data, we've done bio. Next up is physics. And I mean, you can't come to Caltech without having some physics talks. And so CS plus physics is what we'll hear about now. And I already gave, the tie to Feynman, the required picture of Feynman in every Caltech event. So we're covered there. I don't know if they're gonna have one as well. But we have two coming and telling us about quantum interactions with computation for the next hour. So the first speaker is Tomas Vidick. It's all yours.
Thanks, Adam. You clap at the end of the talk, not before. So, but first off, though, let me say thanks to Adam and thanks to all of you alumni for coming here, because it's really for me, like as a young faculty here, it is really truly a pleasure to have the opportunity to speak in front of you. The way I think of it is that what it means for me is that my research, the kind of things that I do here, are not only exciting and appealing to me, of course, but also to you, alumni who went through Caltech many years ago, and since then you've done so many different things, but still you come back and you're interested in that research. So it, makes me feel good. I hope I make good of your time. So, and okay, the other good thing is that because I know that I'm talking in front of an educated crowd, I know that each of you already knows what a quantum computer is, what quantum computing is about, so I'm going to be able to dive right in. I'll explain the picture later. Well, let me show you what I meant. What I meant is that surely you open the newspapers once in a while, and you can't have missed these headlines, right? It seems that quantum computing is quite a hot topic these days. You open even the New York Times, and they make the headlines. You hear about Google's plans for quantum supremacy, for building a quantum computer. It's not only Google, you also have these Canadian startups that are in the business selling these devices. Even Microsoft is in it, and they have their own plans for building a quantum computer. Here's the big question, right? Has the age of quantum computing arrived? And you can wonder whether this is the case or not. I think it's hot enough a topic that even senior politicians feel like they should have. I don't know if you saw that story. I mean, so there was a big. So Justin Trudeau was explaining, Canadian Prime Minister, what quantum computing is about to the journalists, and it's actually not bad. He does a pretty good job. But even if the Prime Minister thinks that there's something to say about quantum computing, certainly it must be hot. So it's IBM is also in the business, and so what you can notice is that all these stories kind of have the same form. So there's three elements. So first of all, of course, you need a catchy title, right? I mean, you can't blame the journalists for that. They have to sell, so you have a catchy title. Then you have like a fancy picture. Kind of like blue and maybe some green and red, and it could involve a laser, a fridge, some kind of stuff there. And then there's some text, right? And the text is kind of sort of like make you go through what's a quantum computer. And I like this one because the journalist is brutally honest, right? What he or she is writing is that what's a quantum computer? Well, it's an enormously complex, sometimes downright confusing technology that's typically the domain of hardcore academics and organizations like Google and NASA. So I hope that after this talk, you don't feel like them. You think that it's not only for hardcore academics, this is really something for actually, I'll show you later. This is really something for everyone. So I will try to make it more palatable for you throughout the talk. But they do have a good point, though, which is that even to people like me, computer scientists, even to physicists, in the end, what's a quantum computer? Is something that looks like this, right? This is one you can buy on the internet. It's I think it's like $10 million or something. So you have, but then it gets delivered, right? And you have this big black thing that's delivered in your living room, and then that's a quantum computer. That's what you're told. You paid 10 million, right? It better be. And so for that price, it'll come with a lot of guarantees, right? It'll come with a little leaflet that says that inside that quantum computer is a big fridge, and then there's some fancy equipment that justifies the price. But typically, it'll also come with a warranty, right? And the warranty says, don't open the box, otherwise you lose the warranty. So, from your point of view, there's a question. You invested 10 million in the thing, and that's what the leaflet says. But then if you can't open it, it might just be this, right? Because this is who you are, right? You have the device, it's a quantum device, but you're like me, you're a classical being, and so the best thing you can do is really push buttons, and you have this kind of interface, and you read numbers, and the question is, well, are you going to think that your money was worth it or not? So how do you test this computer? So that's the thing that I want to talk about. It's quite an actual problem. So what's the difficulty at heart? It's what makes quantum computers interesting in the first place. It's the fact that they have this exponential complexity scaling. So why do we care about quantum computers? Because there's certain tasks that they can achieve much, much faster than classical computers. A typical example is Shor's algorithm for factoring. And the reason they can be so fast at certain tasks is because of this scaling. The number of degrees of freedom of a quantum computer scales exponentially with the size of the computer. So that's the boon of quantum computing, but it has a flip side. The flip side is, how do you characterize the device? If it has so many degrees of freedom, you can't even write down, even in principle, on a piece of paper or a computer for that matter, a classical computer, what the state of the quantum computer is. So then there's sort of two scenarios. One you can say is, well, if this computer really is so powerful, let me just ask it to perform this powerful task to factor numbers, and if it achieves the factoring task, then I'll be convinced that it is a quantum computer. At least it's achieving something interesting. That's if I have a large-scale quantum computer. We don't have large-scale quantum computers. The kind of things that we have are these medium-scale devices. And these are kind of in a regime where it's not obvious that they offer noticeable computational speed up for well-defined problems such as factoring. But still, so they're too small for that, but still they're large enough that we can't do a direct simulation. So we don't really know what they do. We can't simulate it directly, and they don't do something that's obviously useful. And so the question is, how do we test these machines? Because surely, we do believe that they're doing something interesting. They're demonstrating some quantum phenomenon. I'll tell you something interesting that they do now. And so the question is whether we can test that. So I want to tell you a little bit about that, but before I go too much into it, I should tell you what's a quantum computer. So I thought of many ways of getting out of this. One way to get out of it would have been to show you the video of Justin Trudeau. And it is good, you should check it out, but you wouldn't get that much out of it. So lucky for me, I have a better resource. So I'm going to show you a little cartoon. And I'm lucky enough that we do have here at Caltech a very big center in quantum information. It's called the IQIM, Institute for Quantum Information and Matter. It groups physicists, experimental and theoretical physicists, mathematicians, computer scientists. So we're all grouped within that institute. It has a nice logo that's very appropriate to the talk, I think. So nature is subtle. Also to this day, right, is something that you're seeing throughout the talks, this subtlety of nature that we're trying to understand through computer science. And so what IQIM, I think that's a bunch of us going on the retreat. What IQIM also has is that it has a very nice outreach component. So you can check the IQIM website. And one of the things that we do are cartoons. So there's a collaboration between IQIM and, for those of you who know Jorge Cham of PhD Comics, so maybe some of you know. And so they make these fantastic cartoons that are addressed at kids or adults, anyone interested in quantum computing. And so let me show you, I hope this works, just a little excerpt from one of the cartoons, but pay attention because this is going to be important for the remainder of the talk. It's just about 1 minute extract.
A quantum system, a quantum computer can do things, can perform tasks that we couldn't hope to perform with ordinary digital computers. You can't dream of doing it. So when we think about how quantum information is different from classical information nowadays, we're thinking about this intrinsic randomness, the uncertainty principle, and also about entanglement. Classical information we can express in terms of bits. You can take any amount of information and just write it as a string of bits. And in the quantum case, we call them quantum bits or qubits, and they're different from ordinary bits in some fundamental ways. So a classical bit, I can write a 0 or a 1 on the table and everybody can look at it in the same way. But in a quantum bit, there's more than one complementary way to look at it. So you can kind of picture it this way. You've got a box and you can put an object in the box. In the quantum case, there's more than one way to open the box. And you've got to make a choice. If you open door number 1, you'll never know what would have happened. It cannot be known what would have happened if you had opened door number 2 instead. Those are incompatible things. That's something really new compared to classical physics. That's what I mean when I say it's really intrinsic randomness. It's not that there's some record somewhere, but you haven't looked at it yet. There's no record. It hasn't been decided yet whether it's going to be a 0 or a 1. It's not until you make the observation and open the door that it becomes the value of this bit. Maybe it's a 0, maybe it's a 1.
All right, so it stopped here. There's more. I'm sorry, I was going to ask the audience, so you recognized, right? Right, so the voice there is my colleague John Preskill from the physics department. And the other voice, I don't know if we heard him, but the other voice, if we heard two voices, this is Spiros Mikalakis. So he's actually the person in charge of outreach at IQIM. So he's the one who makes these, who designs these videos, not the drawings, but. Okay, so this is as much as, I don't want to give you too much. So there's a little bit of intuition of what's going on with the quantum computer, but I want to focus on just one aspect that's pointed out in the video. It's this notion that quantum mechanics and quantum computers have intrinsic randomness. So for the remainder of the talk, we'll try to understand what this means and why it's interesting. So why it's interesting, randomness is, in computer science, we tend to think of it as a resource. So it's something that's used by our algorithms. You have better randomized algorithms than deterministic algorithms. It's also used in simulations of physical systems or random walks, Markov chain Monte Carlo simulations. It's also used in cryptography. And there it's really important, the randomness that you use in cryptography, you need very good randomness, right? Because any kind of bias that's in your randomness, this is some advantage that you're giving for free to the person who's going to try to break the crypto system. So for all these applications, especially the third one, it's really critical to have a very good source of randomness. And now here we are, we have quantum mechanics, and the video tells you there's this notion of intrinsic randomness. So this gives us the idea of creating a random number generator based on quantum mechanics. Here's how it would look like. You'd make up this little laser there, and then there would be a mirror and some receptors. And then depending where the photon goes, you'd output a 0 or a 1. So you have a very simple, quantum mechanical principles behind such a device are very simple, and there it is. It produces random bits. This is what quantum mechanics predicts. There's a subtlety here. I want to emphasize, what does it mean, intrinsic randomness, right? What do you really mean, intrinsic? So here's one way to put it. I'll let you read the cartoon, but it's pointing the finger right on the difficulty. The same point was delivered maybe more sharply even by von Neumann. And this is what he said, and it's very true, right? So there is no such thing as a random number. There's only methods to produce random numbers. Of course, what do I mean that this string here is random? This doesn't mean anything. This is a particular sequence of bits. It's not random. It's deterministic. The randomness, if there is randomness, is in the process that generated it. So it's in that sense that we want to say that quantum mechanics is intrinsically random, that it has processes such that these processes must be generating randomness. Now I want to use this in order to make a quantum random number generator, but now I start facing the flip side of quantum mechanics, which is what I'm really going to construct is, I hope this is what I build, but from the outset, this is what it looks like, right? It's a black box. And this black box, who made it? Even without taking an adversarial perspective, there is some company, or these are grad students at the IQIM, probably one of those could make such a device, but then do I really trust them, right? Yeah, I mean, they're IQIM grad students, they're good, right? I want to trust them. Do I want to trust them to the extent that I'm going to use that randomness to encrypt my credit card number? Now you're talking some different, right? And just to make this concrete, so as Adam mentioned this morning, so I'm teaching quantum crypto this semester, and it's in the class here in Caltech, and it's also offered online. And so all the students come and you hear quantum crypto, and it sounds like, does this thing exist or not? So I wanted to show them quantum crypto is real. So what we did in the first class is that I went online and went to the ID Quantique website, and that's a company based in Switzerland, and you can buy quantum random number generators. And so I ordered it. I got it 1 month later, so I wanted to show it to you just to make you feel how it looks like, and that my picture there of a black box is not so far off from the truth. So this is how it looks like, pretty fancy. I can, if anyone wants to look at it later, I can show you. So you get this in the mail, shipped from Geneva, and you open it, and that's what it's like. This is a quantum random number generator. And there's a USB thing. I plug it into my laptop. No, I mean, and there's a piece, I could have shown you, there's a piece of software, and then you press start, and then a bunch of random numbers shows up in the screen. It does. I have a warranty here. It's signed and everything. And I can't open it. But I mean, it's so. Can anyone guess how much this costs? Not far. A bit less. 1,000. They go for the sharp numbers. 3,000, you get the faster version. There's a PCI version that's faster. I got the USB. I got the cheaper version. Um, all right, but then the question is, I mean, I did spend $1,000 on this, right? And then what happens? I press a button, and then I can run statistical tests, and the tests are going to say, yeah, sure, these are random numbers, but do I believe this? I mean, there's statistical tests, right? For any test, there's going to be some device that passes it. And this was shipped via FedEx from Switzerland, right? It's supposed to be a laser and mirrors in there, and you can. Is it? There's going. Who's telling me that it's not biased, right? So the question is, you have these miraculous quantum devices that are achieving certain feats, like perfect random number generator. And the question is, how do you test this? What kind of guarantees do you have? And so now we had a problem, which was, how do you generate randomness? We got a solution. Quantum systems generate randomness, intrinsic randomness. And we got another problem with that solution, which is, how do we check that this is the case? And to find the solution, we're going to go deeper into quantum mechanics. So I'll show you the solution. I'll show you that quantum random number generators can be tested in ways that classical random number generators could not be. And to understand that, sorry, so this is the question. To understand it, we need to go back in time to the sort of dark ages of quantum mechanics. So this is the 1930s and the famous EPR paradox. Einstein, Podolsky, and Rosen wrote a paper in the 1930s where they observed that there was this randomness that was intrinsic in quantum mechanics in the ways the laws of the theory were formulated. And they weren't too much bothered by that. Randomness, that's okay. What they were bothered by is the fact that this randomness seemed to come as a necessary corollary of a much stronger phenomenon. And this is what is now called, I think Schrödinger coined the word, entanglement. And so what they observed is that quantum mechanics lets you prepare systems in a way that there's two systems, think two photons, in a way that when you put the photons far away apart and you perform measurements on these photons, the outcomes of the measurements are correlated in ways that appear to be stronger than what would be classically reasonable. At least they seem to violate some kind of reasonable formulation of locality that you would have in mind. But it's not obvious that something is wrong, because when you look at only one of the numbers by themselves, the outcomes, these are just perfectly random, uniformly random. There's no problem with generating uniformly random things. You can flip a coin, that's okay. Everything is in the correlations, and these correlations by themselves don't obviously violate causality or non-signaling. There's no signal going on because of this randomness that's there locally. And so that's why you can debate a lot about this, and you can say there's these correlations, I don't quite understand, are they reasonable or not? And there was a long debate. And so there's different approaches you can take. You can be a theoretical physicist like these guys, or a philosopher, and you can talk and talk. Or you can be an experimentalist, and you can say, look, I mean, if the theory says that these correlations should exist, let me do an experiment and check, right? And this was done from the 80s, so this is in France, until just this year, 3 experiments were made. This is one in Delft. There were 2 others that convincingly demonstrate that these correlations do exist, right? So all loopholes barred. There's no excuses now. We know that these correlations exist. Fine. Now that's good, but yeah, what about John Bell? No, so okay, I'm getting to John Bell. This is interesting, but I was exactly getting to your point. So this is a bit different. John Bell was not an experimentalist; he was a theorist. So the experimentalists demonstrate the correlations, but what I was about to say is that the fact that you see them doesn't make you understand them better. What do they mean? What's going on exactly? And that's what John Bell put his finger on. He started off, between 35 and John Bell in 64, no one understood anything. Then John Bell came around and he said, look, let me formulate this cleanly, mathematically. I want to understand what these correlations are and why, what's not reasonable about them, or what's rather surprising about them, but why still they're reasonable. They don't violate any of the physical principles that we're used to. I want to give you a modern formulation of John Bell's interpretation, which is the CS formulation, which is, how do you understand something? You can do experiments, observe it. In computer science, we have this language. We have these questions, these concepts that we can use. For instance, the concept of randomness. And now we want to understand correlations, entanglement, through this angle, by asking this question, by asking where does the randomness come from and how would we use it? So let's do that. So this is a modern variant of John Bell's formulation of the EPR experiment. And I want you to sort of forget things that I said. Remember your undergrad days at Caltech. I don't know how they were. Maybe they were a little bit geeky, right? This school does have a reputation. So I'm sure you liked puzzles. So here's a puzzle. So I'll formulate it as a game. So what's the game? It's called Magic Square Game. It's due to Mermin-Peres, so it came a little bit after Bell. So imagine that you have this 3x3 square, and there's two players, Alice, and then there's going to be Bob. And what they're tasked with is that Alice is going to be assigned one of the three columns of the square at random, and she has to fill in values 0 or 1 for the entries of the column, such that the parity of the entries should be odd, right? So she can be asked, she's only just asked one of them, but it could be any of the three, and then, so pretty easy, right? At the same time, Bob, who is Alice's friend, but is in a separate location, is asked for a row. And again, he has to fill in entries for the values for the entries in the row, such that the parity of the entries now is even. And there's one last requirement, is that these two guys should agree. So whatever the column and the row, they're going to be intersect in one position, and then they should give me the same value in the position. That's the things that are checked. So Alice could be asked any of the three columns, Bob any of the three rows, but only one of them is going to happen, right? But they have to decide on the strategy. And so if you think about it, because each square is always the intersection of a given row and column, if they want to always win this game, before the game starts, they're just going to have to agree that they're going to answer consistent answers to all possible questions. So basically, the task of Alice and Bob is to come up with a labeling of all 9 entries that satisfies all 6 constraints, the even and odd parities. So we can try to do this, right? So let's do it. So I did it for a row and a column. Let's do it for the first column for Alice. So this is okay, right? Odd parity, we're good. Now we can do the first row for Bob, even parity, I got it. Okay, now I only have 1 entry left, and I need the column to be odd in the row. Okay, someone saw it, right? I'm stuck, I messed up. So am I dumb or is there a problem? So do you know? Can you do better? I could, backtrack. Maybe I messed up, but okay, the more mathematically minded will notice that I cannot do better. It's not me. It's the game that's sort of designed against me. I can't do it because the problem is, look at it. The rows all need to have even parity. So if I take the parity of everything, it's going to be even, right? The columns need to be odd, and odd plus odd plus odd is odd. So the columns tell me the sum of everything should be odd, and the rows tell me the sum of everything should be even. That's just not possible, right? So I can't do it. So stupid game, right? I can't win. So fine. So the best success probability 8 by 9 because there's 9 questions, 3 rows, 3 columns. Okay, now here's what Mermin-Peres observed is that if you change the rules, you don't change the rules, but now you allow Alice and Bob to be quantum mechanical. So, before I allowed them to meet and agree on the strategy, right? This assignment. When they meet, they can prepare photons, and Alice leaves with her, Bob leaves with his photon, Alice keeps hers. There's no way I can detect that, right? She's just, in her pocket putting a photon. And what it turns out is that if they have this resource, entanglement, that does not allow communication, it does not violate causality, then they can win in this game with probability 1. And I find that amazing, because this game is impossible to win. It's the same game as before. There is no way to fill in the entries of that square. I didn't lie to you. But using quantum mechanics, they're able still, anytime I ask them a pair of questions, they're going to give me valid answers. But the way they get away with it is that they're only able to answer one pair of answers. If I asked them, repeatedly measure your system so that you could tell me what are the 9 values, they wouldn't be able to do it. They do it once. One measurement on their entangled state. It always satisfies the constraints for the row and column that I asked them, but then that's it. It stops. They made the measurement. So now here's the deep observation. But simple. The observation is as follows. It's that now we have a test for randomness. Because the thing is that if you play that game and you are able to succeed in that game all the time, even if I have no idea what you're doing, I don't even need to know that you're using quantum mechanics or not. The only thing I know is that you're not communicating. If it was the case that you were using a deterministic strategy, then you'd be able to fill in the 9 entries. I'd ask you, what are the 9 values? All possible questions. If you're deterministic, I can do that. But then you can't win all the time in my game. So if you're winning all the time, you must be doing something that's not deterministic. Could be quantum. It could be what, this I told you could do, or it could be something else. I don't care. I don't know if this thing is quantum or not. If it wins the game, then it's producing randomness. That's the only way you can succeed in that game. So I think what's my time? I'm running out already? Couple minutes. So I'll just sort of, I guess, zoom out and tell you how this is used as a test for randomness. So we have this random number generator, my black box. So I'm going to ask a little bit more, right? There's Alice and Bob, and I do need one more constraint, which is that I buy not only one box, but 2 boxes. and one is going to go with Alice, one is going to go with Bob, but they could be in the same lab, right? The only thing I need is I need to convince myself that there's no communication between these two devices. And one way to do it is to do the experiment fast enough that light just doesn't have enough time to go from one device to the other. And then I'll be convinced that there's no communication. Could be entanglement, could be not. I don't really need to know. I need to know there's no communication. And then my test will be this. I'll just ask my random number generator to play in this game. So I'll input questions, column then a row, collect answers, repeat this many times, and check. And if the answers that are provided are always correct, then I'll know that this device must have been producing randomness intrinsically. It's not that this particular sequence that it generated, it could be a sequence of all zeros. And then I'll just say, fine, it's a sequence of zeros that was produced randomly, and that kind of thing can happen. You know, it has a certain chance of happening. So that's our test. And in that sense, now you have a random number generator that's Einstein certified. Even the biggest quantum skeptic has to believe that there's randomness, because you don't need to trust the quantum mechanics. The only thing you need to trust is relativity, which Einstein surely trusted. So I wanted to argue that this could be used further. It's not only randomness, it can be used for cryptography, so you can get proofs of security for quantum key distribution that are based on this, but I'm running out of time, so I'll skip ahead in this slide. I didn't want to show you my picture, so maybe ignore the slide, but focus on the picture. It's one further property of entanglement. So entanglement lets you generate randomness. Randomness is good, but for cryptography, you want more than randomness. You want that the randomness is not only local, but is also secure. It's private randomness. I want to have the guarantee that no one else knows my randomness. Because if someone has a copy of my random bit, it's no use. They have a copy of my key. And entanglement has this further property that it's monogamous. So it has this property that if I have very strong correlations at that level between Alice and Bob, this precludes correlations of a similar strength with a potential eavesdropper, Eve. So this is an even deeper property, so this monogamy of entanglement that we exploit. This is what I actually work on, this device-independent QKD, and so we work in trying to understand this monogamy of entanglement in order to get proofs of security. But let me end from the start. So Adam was right. I did steal a picture of Feynman. It's impossible to talk about quantum computing without showing you Feynman. So I just wanted to broaden up a little bit at the end to give you a little excerpt from a speech that Feynman gave at Caltech in 1981. So Feynman is credited for having the idea of basing computers on quantum mechanics. And here's the way he put it. He saw two sides of it. He said, you know, why do we want to do quantum computers? For two reasons. One is that we're going to learn something about computing because we're trying to base computing on physics. We can see how far we can go. But it's only that. It's not only that. It's also about understanding physics by putting it in this computational framework and asking computational questions. And this is something that Xie is going to tell you much more about in the next talk, what kind of interesting physics come up when you try to realize quantum computers. But I stop here. Thank you.